Now, internal force. We want to find at point C what are the normal shearing and bending moment is. Now, what I did, I cut the structure at point C, and then wherever you cut it, you have to stitch it. The way that we stitch it with NVM. Normal force, shearing force, and bending moment or shear force. Now, what I have left in this case, if you look at the structure already has a triangular load that going up there. Now, how much the bending moment changes? Like if this structure wants to collapse, again, if you assume the same thickness from A to B, right, across the whole beam, where has the highest bending moment in this structure? From where this structure will break? Anybody has any idea? It will break from point A, B, or C. And you have 3 attempts. Okay, use your engineering sense. This guy is break from point A, B, or C based on the load shown. Will be A, exactly, because you have the maximum moment there, right? All those little forces, they add up and they become too much there. Now, in this case, I'm looking at point C, okay, and then I draw the free body diagram only for the right side. Now, how much the height here would be? How much would be the height here on the load? Your maximum height here is 1200, right? So we can use similarity between triangles. The height here is 1200, the whole length is 3, down here is 1.5. How much the height here is going to be? Again, we go back to the 5th grade. Yes, 600. Yeah, this will be 600 Newton per meter. So the height here is 600 Newton per meter. It becomes very easy. Now I can deal with it, right? I have the height and the base is 1.5. Based on the lecture I gave you a few minutes ago, you can actually convert this distributed load into 1-point force. Again, this is a distributed load. We want to convert it to 1-point force. That 1-point force, the amount of it will be 600 times 1.5 divided by 2. Because, again, remember, this is a triangle. So it will be half of 600 times 1.5. The answer is 450 Newton. Now, where I put it from half of here. So in this case, it's 0.5. That will be, sorry, 1/3. Oh, my bad, 1/3. So 1/3 of 1.5. The answer is 0.5. Now, how can I find NMV? Very easy. You just do sum of f of x equal to 0. From here, normal force is 0. Sum of f of y equal to 0. I'm going to get V minus 450 equal to 0. So your shear force, V is 450 Newton. If I want to find the moment, what I'm going to do, I'm going to do the moment about point C. That's the easiest way to take care of it, because N and V are gone. So we have minus M. Again, either I use minus M or just the way M it is. And 450. So 450 is going to go clockwise. Minus 450 times 0.5. The answer for this, equal to 0. M is equal to 450 times 5 is going to be 225. The positive 225 Newton meter. That's how we calculate internal forces. Now, stuff could become more confusing if they ask us not only in one point, but across the whole area. How can we do that? So we know stuff are changing, and then when things are changing, how to deal with it. I guess it's in the back of this, or maybe, yeah, I have it here. So let me flip the page, take this problem, go to a different problem. Okay, in a problem like this, if I want to find bending moments, I know, like for instance, I can convert this to a distributed load, but assume that the question asks me to find the bending moment, shearing force, and all these things in multiple points. Like assume that I want to find it in this point, point A, B, C. I'm going to call this D, point E here, and point F here. Now, if I want to do it like that, so you can see from point A to E, again, overall this is 8 feet. I'm going to assume here is 2 feet, here is 2, here is 2, and down here is 2 feet. Now, if you look at just one location down here, one location at the A, everything is 0. Shearing is 0, bending is 0, because if you cut it from A, nothing would be there. So if I do AE, A and E. A to E is 2 feet, right? This is A, this is E. At the point E, I'm going to have 3 force. Again, forget about the normal force, because in this case, we don't have normal force. We just have a shearing. So I'm going to put V up here, and then a bending moment like this. And this is actually V, direction of V is up to you. You can put it in any direction you want. So the height here is 120, the base here is 2 feet. So if I replace this with one force, I'm going to get 120 so it's going to be down here. So it'll be 120 times 2. You put it in the middle, right? Which is going to be 1 meter from here. And this is 240. Now the value for V, right? If you do sum of f of y, you're going to get V is equal to 40 pounds. Now, if I go back to, again, this was from point A to point E. If I cut it at point D, so I have a little bit longer, right? A little bit longer, V is like this. Then we have a moment here. So in this case, the V was 40 and the moment M. Now I have the 140. Again, this is going to go that way. This is going to go counterclockwise. So M plus 40 times 1 is equal to 40. So I'm going to get 40 pound-feet on the moment in this case. Now if I move on more, if I move on to the second point, distance here becomes 4 feet. The force become, if you put the force in the middle, the force would be 120 times 4. Sorry, this 120 times 2 is not 40. It's 240, right? No one told me that's 240. 240, 240, this will be 240. Now down here we have times 4, which is going to be 480. Now you can find a relationship, right? This guy is sometimes going up with some respect. Then your M would be equal to, this distance is 2, so it will be 480 times 2, and then will be 960. I can calculate it for the other areas for multiple points like this, then I can graph it. But this will be too much work. That's where I can just use a different method. In this method, I'm going to just assume this distance is X. If I have the load like this, and this distance down here is X, we have a force V like this and a moment like that. So if I want to replace this force, I can replace it with, again, this down here is the height of it, whatever the height of it, in this case is 120. So I can actually replace this with something here, 120x, and the distance from here is half x. So you can say V is equal to 120x and M is equal to, so again, if you do moment about this point here, again in this case I'm going to assume this point is point O. If I do moment about point O, I'm going to get 120x times the distance is half x, so it will become equal to 60x squared. Now if I want to plot the bending moment and the shearing force from this point to this point, the plot is going to look like this. Again, your load was like this. Was 120. So otherwise I can just have a graph like this, and then I'm going to say the force was 120, right? That was the amount of force was. This was the load, sorry. This was the load. But again, on the shearing force, shear force, we have it as 120x. So again, if you put x at the end, 8, so 120 times 8, it will be 960. So at the end, it's going to reach to 960. And at the beginning is 0, right? Because your x is going to go from 0 to 8. So that's how the shearing force look like, starting from 0, reaching to 960 at the distance of 8 feet. And then the bending moment is going to look like you start from here and then you go quadratic up. And this is 120 x squared. If I want to find the value here at the point 8, so I'm going to say 120 times 8 to the power of 2, which is going to be 7,680. But again, I'm not going to require you to do any calculation like this. We have a code that we're going to use it, and it will take care of this calculation for us. But I just want to show you the details of it. It keeps changing. Basically, in this figure, you have the maximum shearing force at point C. No, maximum shearing force is anywhere between here, right? So it's shear, because from B to C, the shearing force won't change. But your bending moment, the maximum will be at point C. Let's move on to the project, and then you can go to breakout rooms to work on that.